Uh, Thank John and Kenny for organizing this meeting. I'm very happy to be here. I really new, to this community. I think unlike a majority of you, are really doing the fundamental science of, related to air quality. Probably it's very old of this topic, but my purpose is really to understand how the aerosol growth, interfacial role in the growth of aerosol are related to air quality. My background is spectroscopy. My research interest is to develop and use nonlinear optical spectroscopies to understand the fundamental issues related to environmental chemistry. One research we're doing now is how we understand the interfacial composition of aerosol particles. I will show you why it's important. Okay, here. I really appreciate this idea was initiated, I think, 10 years ago when I worked at the Columbia University, but no one trusted me when I proposed it. This is why I just got a job last year. But I really appreciate the Utah people for recognizing this topic because this is very important. I hope I can convince you. This work is collaborated with Phil McNeil from Columbia University. Okay, so in this community, I don't need to mention the significance of the aerosol, how the related to the air quality. But I do emphasize the interfacial role in the growth of aerosols related to the PM 2.5. Okay. Just give example here. Let's look at this aerosol particles here. So you will see the particle inside there are many chemical species. You see all the inorganic species, organic species. So all this part can absorb the surface particles. In the meanwhile, in the gas phase, you have organic pollutant radicals react edges. So this also can diffuse and absorb the surface. So basically, this surface is not simple. It's a simple place to hold molecules. But because this surface is exposed to the light, and also concentration is enriched at the surface. This is why the reactions is much faster than both in gas phase and aerosol particles. So the reactions in gas phase and the aerosol particles are well documented. You can find the data from any handbook, but no data from interface. So my interest is to focus on the interface role, how the interface photochemistry take place at the interface, because especially in the small particles, aerosols. Okay, so I'm going to show you how we use some frequency generation and second Harmonic generation to tackle the problem. Why people wait for me to do this? Okay, but I just give a very brief introduction about some frequency and second Harmonic generation. Okay, so before that, I want to show you my scientific objective. So idea is I want to understand the chemical composition and the reaction at the aerosol interface in situ directly. So I want to bring my laser, my detector, go to the plane or car, or just the speaker mentioned. So to monitor what's going on at the interface, particle growth, not only particle inside, but how the interface play a role. Okay, to reach this goal, not easy. I hope before I retire, I can reach this goal. Okay, but don't get to the point. I hope the funding agency don't get, don't rush me, but take your time. Okay. So idea is I'm going to use the laser to monitor this aerosol growth at a starting point, because this is very challenging. The goal is very ambitious. I'm telling you. Okay, so I started from second harmonic generation because it's easier. Okay, why easier? If you're interested, you go to the poster session. I will show you. So first of all, I want to show you how do you know you observe the particle at the interface? Even this very, very simple question, no one can demonstrate. Okay, I'll show you. So I will use this DA4 molecule to see, okay? Let's see how decide to do. Okay, for some frequent generation, usually with 2 lasers. So for the planar surface, basically, by satisfying energy and the momentum conservation, you have some frequency radiative, very directional. However, but second harmonic generation is special case of some frequency generation. We just use 1 laser to do. As a second order process, some frequency is very interface specific. So only measure the surface or interface. Okay. So good part is in the past, people use this method to detect the planar surface. But I know I got interviewed by several environmental community. No one trusts the air-water interface. They want to see the particle, even find the edges. I will tell you, how find the edges get excited after I give a talk. So the good part is quite a while ago, they have, this is the well-recognized paper, people to use some frequency to study all the composition for surface for Amazonia, California. But what usually people do is they go to field, they connect the aerosol, then come back, put a substrate to see what's going on the surface. But no one trusts, because during this process, transportation, chemical and physical property of aerosols get lost. So in this case, find edges said, okay, or committee said, we want to see the interface directly in situ, and also we want to track the kinetics and the dynamics. So we have found a way to do it. So good thing is that this in principle, people already demonstrate. Okay, so the idea is, usually I just said, the surface is non-central symmetric. So this is why we can use a second harmonic or some frequency to do it. However, particle is the central symmetric. Why you can measure, right? In principle, you find if your particle is very, very small, yes, it's central symmetric. But its particle is much bigger, is 10 nanometer or bigger, then you will see the non-vanishing second harmonic generation or some frequency generation. Okay, principle is here. Now, how to implement this idea? So I will show you how we do. Okay, so like majority of you, we just generate the aerosol in the lab. So we just use this atomizer to get this around 100 nanometer particles. Let's see what we can do. So we use sodium chloride as a seed. Then we put DA4. Okay, by the way, in this case, I'm pretty sure this is PM2 too high, right? So over the range. Okay, at this point, I will show you how we do. Okay, then this setup we just use atomizer generate aerosol, this chamber, then we use laser to do it, to detect. Okay, we don't need to go through all the detail. If you're interested, my students here, we can discuss in detail. Okay, let's see evidence. How do we know we see the signal from the aerosol particles? Okay. So we can do experiments. We do in solution, put this sodium chloride without particle. You will see the blue line. Okay, the 2-photon emission spectrum. You will see at 400 the peak, there has a 40 nanometer another peak. So this peak is due to 2-photon fluorescence. This one is due to the Harmonic scattering, due to the number fluctuation of incoherent second harmonic generation. Okay, you will see the ratio of Harmonic scattering and TBF is 1:8. Then you shine light at the aerosol particle. You will see the signal is opposite. So this peak the ratio opposite is 10:1. So if this signal from bulk, you will see this ratio, right? But we see opposite. So this really demonstrates we see molecules at the interface. So I think this is a big step towards the research goal. Okay, even this really little bit small. I think the Utah people recognize this. Okay, right away they hire me. Thank you for hiring me. Okay, now we move forward. Okay, we just show you the second harmonic generation active molecules. Now, because we see organic acid, all the molecules not the second harmonic inactive. How can you measure? So the idea is we just use CTAB or to measure, compete with them. Okay, competition. I will show you how we do it. We just add CTAB into this CTAB and DA4 molecules compete. You will see the CTAB, the aerosol surface. You will see the decrease. Okay, keep going. Okay, now the question is, give the challenge to theoretical people. There was gas aerosol particle interface, same as the air-water interface. So due to time limit, I will just show you the answer. Okay, you see the comparison. It's air-water interface, you see the very sharp decrease as a function of concentration. But the aerosol particle is smaller. Okay, turns out the difference. Okay, I will not show you all the evidence because it could be due to size, temperature, molecular orientation. It turns out size, orientation, temperature is not the issue. Orientation also not the issue. And size matters. Okay, so we think because the smaller the size, the lower the surface free energy. So because this surface curvature or affect the bonding constants here. So to summarize my talk, we may have made the direct observation of organic molecules, and the surface bonding CTAB at the aerosol is smaller than planar surface. Surface curvature is a major possible reason for the difference at the air-water interface. So two years ago, I give a talk, similar audience. Then right after, there's a funding agency from ARO. They came to me, the project manager, said, do you need more money? I said, of course, yes. So I hope today have some people coming to me. Okay, I would like to thank my students who did all the hard work. Thank my funding agency. Thank you for your attention.
Okay, thank you very much. And we probably have time for one or two questions.